Hey, my name is Mayanga Unit, working with Nahiroza Alvin, and this is machine learning with Python. So, first off, machine learning is a field of study that gives computers the ability to learn without being programmed. We have two types of machine learning: supervised and unsupervised. With supervised, this deals with labeled data sets, which gives the machine learning algorithm a labeled data set from which it will learn from. And unsupervised machine learning, we have unlabeled data set. So that's just the basic difference. So we have clustering and unsupervised machine learning, just grouping features together, which are the same characteristics, some anomaly detection, unusual occurrence of a data instance in a data set. For example, outliers, like data that is way too far from the all other data sets in case of flood. Uh, we have machine learning pipelines. These are just like the steps followed maybe in when you're performing machine learning. You get the data from the field, then you perform an exploratory data analysis. It should be quick, efficient. You don't have to take a lot of time on that. Uh, you prepare the data for machine learning algorithm, clean the data, make sure it's perfect and good quality, select a model and train it, fine tune your model, present your solution, and then launch, monitor, and maintain your originate. So I'm going to talk about feature scaling. This says whether the model performs well or not during the training. So under feature scaling, we have normalization. Just fix a range of data between values, -1 to 1. Perform standardization, transform the data to have mean of 0 and a standard deviation of 1 to control the spread. Um, the values of the feature should not have big difference between them to prevent the, the model from being biased. There should be a standard range in which values of all features should lie. So scaling just helps the graded descent or like the algorithm to converge fast. So when to do scaling, when using machine algorithms to calculate distance of data, neural networks, k nearest neighbors, for example, like clustering, the algorithms that are rule-based, random forest, naive Bayes, not require feature scaling. Yeah. So we have data cleaning. You prepare the data for the machine learning algorithm because you have to give it quality data. So here you remove the duplicates and irrelevant data. So if you have any missing data values, you're either going to drop them or completely remove them like from the data set. Or you may do imputation whereby you're going to replace them by finding the mean of the data that you have and then replacing it with what is missing. So to balance the data set, you can remove features that would impact the solution. You can add or create new features from the existing ones, or you can combine features that either have the same value and you feel like they're the same, combine them together. So every machine learning algorithm should have prediction model that takes the set of features and predicts the outcome. Cost function that gives the difference between the actual outcome and the predicted outcome. So the actual outcome and the predicted outcome should not have like a big difference. They should not be so far away from each other. That's the use of the cost function. We have the optimizer, uses the iterations to optimize and reduce the cost to get better prediction. So when we talk about models, just a representation of a phenomenon, like anything, any topic or what, you can use a model to represent it. So we have deterministic and probabilistic models. So under deterministic, there is no randomness here. We just deal with exact relationships and a suitable prediction error is negative. So probabilistic, there is randomness, and here they have emphasized two elements. We have deterministic and random error. So as you know, probability, you deal with a lot of randomness and stuff. So yeah, that's where that comes in. So we have types of probabilistic models. We have three: regression models, correlation models, other models. So regression models are used to represent the relationship between one dependent and explanatory variable. So an explanatory variable is just an independent variable. So regression models just show their relationship between a dependent one and an independent one. Regression modeling steps. The hypothesize deterministic component. The outcome must be exact. You must know the outcome, not just something that you predict. Specify probability distribution of random error term. Evaluate the fitted model. Use model prediction and estimation. So in a linear regression model, relationship between variables is a linear function. So like those linear functions like with math, straight lines and stuff. So we have two types of regression models: the simple, which also have linear, nonlinear, and multiple, which also have a linear, nonlinear. The logistic regression deals with classification problems, and the logistic function is used to estimate probabilities, while the estimate function ensures that the value will range from 0 to 1, as we talked about like in the beginning. So I'll let my colleague take over from the parametric and non-parametric models.
Hello, this is Naireza Alvin, and as she has said, I'm working with her. Machine learning with Python. So I'm going to pick up from here where she had stopped. She was talking about models, and as she said, a model is just a representation of any phenomenon. So, and now a model has parameters. So while estimating these parameters, the least square method helps us to get the best fitters. Sometimes you have to plot the data values. Yes. So now the best fit means the difference between the actual Y values and the predicted Y values is the minimum. The difference doesn't have to be so much. The difference between the predicted values and the actual values. Now, parametric model it fits the data using the linear regression. As you can see, that is equation of a line, and it shows you which model exactly will fit the data. We are trying to be brief because of the time. We just looked at the parametric model. Another non-parametric model. In this case, it's the data set that tells you what the regression should look like. If you continue, the function can be perfectly approximated by an infinite parameter. Model specification involves defining the dependent and independent variables, but it is the model specification is based on theory, different kinds of theory. Some of like theory of field, mathematical theory, previous research, so common sense. So population and sample models. This one's you take a random sample from the population. After taking a random sample, you apply regression on it in order to find the relationship. The relationship should be equal to the relationship with the actual population. Yes. Next thing is we're going to talk about the k-nearest neighbors. The main KNN algorithm steps include calculating the distance between all the training data and the test point, finding the nearest k-neighbors by sorting these pairwise distance. Then you classify the point based on majority votes. Yes. So you have data values and you have a test value. So you identify the value of K. Let's say K can be maybe 5. So you calculate the distance from of all the five points from the test point. Yes. So among the 5, you use a majority vote, classify the test point. Hyperparameter tuning. This one we should never use. Test data to do this. The ultimate goal of any machine learning algorithm is to perform well on the unset data. We have to split the data set into 3 parts, as we can't. Yes, we have to split into 3 parts. That is training, validation, and testing. However, in cross-validation, this is when the data set is split into K groups. K can be any number. So after splitting, one group is used for testing and the rest can be used for training. Now, when doing this K nearest neighbor algorithm, as I've told you, you have to calculate the distance between the test point and the other data values. So how to choose the distance measurement? You can use linear distance when measuring similar properties, e.g. width, height. On the other hand, you can use Manhattan distance if the dimensions are similar. For example, if you're measuring age of someone, their weight, their gender. So if all features are equally important, but they are not the same scale, they must be normalized. So some of the KNN applications include text mining, there is agriculture, there is finance, competitions. It has pros and cons. Try to summarize them in the interest of time. First, it is easy to explain, simple to understand, and it's extremely powerful. It does not require any assumptions on the data distribution. It is the first choice when there is no prior or there is very little knowledge of data distribution. And then you can use it for both regression and classification problems. Those are some of the pros. The cons is that among them we have that the efficiency of the algorithm declines very fast as the data set grows. So it works well with small data sets. It comes at a cost of making the prediction step relatively expensive. Every time a prediction is to be made, such as the nearest neighbor in a complete training set, and it suffers from skewed class distributions, meaning if a class frequency occurs in the training set and is most likely to dominate the majority voting, the new example. Yes. Next, we are talking about decision trees. So they relate to making decisions based on questions and answers. The decision tree ID3 algorithm, it has 3 steps. First, you find the best feature. After finding the best feature, you find the best split for the best feature that you found. Third, you partition classes based on the above steps, that is 1 and 2. So the inner impurity measures that the frequency at which any element of the dataset will be mislabeled when randomly labeled. The inner impurity is calculated using a specific formula. It's there. The Guinness index has values inside the interval from 0 to 0.5, whereas the interval of the entropy is from 0 to 1. Entropy, for entropy, it's more complex since it makes use of logs. The calculation of the Guinness index will be faster. The pros of decision trees have easy to interpret and visualize. It has no assumptions about distribution because of the non-parametric nature of the algorithm. It can easily capture nonlinear patterns. The cons, we have sensitivity to noisy data, and also the small variation in data can result in different decision trees. So you can reduce this by bugging and boosting algorithm. It is biased with a balanced data set, and it is a greedy algorithm, as it doesn't yield global optimum tree structure. The simple learning is about combining many mediocre models in one supermodel. And for bugging, parallel training of different models using different bootstrap training sets, it helps in reducing variance of the model, thus reducing overfitting. Boosting sequential training of models by iteratively weighting training samples. So a random forest is slightly modified bugging algorithm. It is basically a collection of decorated decision trees built as follows. For every tree, we subsample the examples of replacement bootstrapping. For each subsample, we choose attributes at random. Randomly pick features in each split. We build a tree only on these random features and current subsample. The random forest process includes robust outliers, works well with nonlinear data. It lowers the risk of overfitting. However, it is biased while dealing with categorical data. It is slow in training. It is not suitable for linear methods with a lot of sparse features. So by default, for support vector machines, by default, they give more weight to correct classification than margin maximization. They can detect outliers and ignore them. So the kernel takes low dimensional space and transforms it into higher dimensional space. Yes. So in the interest of time, I will summarize. The kernel function defines inner products and similarity in the transformed space. Gamma is a hyperparameter that controls the distance of influence of a single training point. Low values of gamma indicate a large similarity radius, which results in more points being grouped. So margin maximization aims at reducing misclassification of data. The hard margin associated with correct classification of data points. The soft margin, data points may not all be correctly classified. In the interest of time, stop here.